more words which need to be done, but this is how the FPGA works. And so this is kind of this instruction set architecture we have, right? So reading and writing to these registers. Okay, so I would say let's start fuzzing, but let's quickly define 3 goals we had in mind during our fuzzing campaign. And first, we want to explore fuzzing as a more general defense technique, right? Because fuzzing is relatively sparsely applied on hardware so far in the literature. So more concretely, we want to fuzz and find in an automated fashion these bugs, and we want to automatically find these vulnerabilities like Starbleed, right? Because finding Starbleed was kind of erroneous, error-prone, and so on. And also more concrete, we want to better understand this configuration engine, as we are generally interested in the Xilinx configuration engine, right? So we want to dig a bit deeper into it. And as I said before, there are these 32 addressable registers, and only 20 of them are documented. And documented doesn't mean they are very well documented, right? So there's like one register where only 1 bit is documented, and then there are 31 bits marked as reserved. So we don't know what they do. Do they have any functionality? Is there any hidden functionality? Or what's about these other registers? Do they even exist, right? Okay, so let's start building our fuzzer, right? And so in this example, we want to fuzz this control 0 register again, right? And for this course, we started to implement confuzz, right? The first important module of confuzz, so our configuration engine fuzzer, is the bitstream mutator. So we want to, in order to test this control 0 register, we want to generate a lot of bit streams with different bit patterns of only this control 0 register in difference. And so we mutate this generated bit stream here. And the neat part about this bitstream mutator is that we can define bit streams in Python code, right? So we have several primitives. So for example, a decryption primitive. So to say this part of the bit stream is encrypted or is authenticated and so on, right? So it's quick, very easy to define new bit streams in this Python code and test different bit streams. And then the different bit streams got generated. And then we have this hardware abstraction layer, which sends the bit streams to the configuration engine. And also, then afterwards it sends the bit stream, it retrieves the state of these configuration registers. So all these 32 registers are read back. And then we evaluate these states with like user-based, some user-based configuration. For example, we test against the default state, right? So we once read back all the 32 registers and then see if there are any difference in these states or not, right? Or if there's a specific bit set or not. And then after the evaluation, we can send this evaluation to the to a web UI, and so the security analyst can see if there's any difference in the bit stream and how the state behaves. Right? Okay, so now let's start fuzzing. But the problem here is that this search space of the registers is quite too large, right? So we have 32 registers with 32 bits, and then randomly testing all these bits. This would be totally inefficient. So we came up with 3 strategies to only test the important bit streams, or the meaningful bit streams, and not every bit stream. And the first strategy is here this bitstream structure strategy. So where we started fuzzing this command structure of the bitstream, right? So this instruction set. And here this is in this table, there's this header command, and there's a lot of bits marked as reserved, right? So in this middle here, there's 2 bits marked as reserved. You have the register address, there are some bits marked as reserved. do they have any functionality? What is about there? And this header type 001 is also fixed. Is there any difference? So what's about this? Then in our second strategy, we target the intro commands. So we want to target all the specific bits in the registers. So we test all the registers itself. So we gain a bit more intuitive understanding of each register and see how it behaves. And especially the undocumented ones, right? And then we have this intercommand strategy where we fuss the behavior between the different commands, right? So we test all the several commands in one bitstream and see how they influence the FPGA states combined. And with these three strategies, we implemented 71 fuzzes, which generated 83 million test cases, and this run in about 2 weeks. So let's discuss our findings. And in general, we better understand now this configuration engine, right? So for example, we can say, of course, to a certain degree of certainty that this register 15 does not exist, because we never got anything back from this register. It doesn't influence anything, so we say, okay, this most likely doesn't exist. This register 26, which was not documented, is this RSA data in register, which is later important for the RSA authentication. And also we found some weird behavior. So here in this register 23, for example, we found a hard crash directly in this register. So a specific bit pattern completely crashes the FPGA, meaning that we have to power cycle the FPGA completely. So, and this was like the only case, right? In all the other cases, it was easy to like send a JTAG command and then it resets the FPGA. But with this specific bit pattern, you really have to pull the power plug and then you can use the FPGA afterwards. So at least we found a bug in the configuration engine, or let's say we can DOS now the FPGA, right? And also, as I said, it was quite easy to test different bitstream patterns. So we have this rapid prototyping feature. For example, during our research, we came across this Xilinx patent describing this RSA authentication mode, and there was a test mode mentioned, right? And so 10 minutes after we saw this in this patent, we sat down and described a bitstream in Python code, and it was very easy. Like after 10 minutes, we could say, yeah, this test mode exists, right? So quickly testing hypotheses about the bitstream in this rapid prototyping approach. And we rediscovered Starbleed, right? So this could also be done automatically. And also we discovered this just start attack. So let's dive into the just start attack and see how this works. So in the UltraScale series, Xilinx introduced this RSA authentication mode, which authenticates the bitstream here, so this orange part of the bitstream, and optionally decrypts it as well, but we will leave this here for simplicity. And again, we will just start programming this bitstream here to see how this works and what the benefits of this mode are. And it starts with this write to the RSA register, so this register 26. And this enables first this authentication engine here. So with now all the bits coming next are first buffered into the FPGA. So they are loaded to the FPGA. And while loading, they are checked. So the RSA signature is checked. And so they are not interpreted yet. So we defend against these time of use to time of check attacks, like Starbleed, and also like classical side channel attacks we can defend against, right? Because we don't decrypt before the RSA authentication is ensured. And we use the fabric here as a buffer because the fabric is like a giant SRAM cell, right? So we have the buffer already there, and we can reuse it here. And then at the very end, there's this rwgo command, which says, okay, now start or finishing this authentication mode. And then only if this authentication is completed, then execute the buffer, which is stored there, and execute the normal commands which are stored there. And there is this usual startup sequence stored, right? So then we execute this usual startup sequence, releasing the fabric, and then the FPGA can run it as usual. And then, okay, so we have this rwgo command at the end, which is not authenticated, right? And which is one of the first commands executed in this bitstream. So why not fuzz this part of the FPGA, of the bitstream? And it turns out that if we substitute this rwgo command with the usual startup sequence, we can just start the FPGA because all the content which is needed in the fabric is already at the right place, right? And it's unencrypted, so it's only authenticated here. So we can say, just start the FPGA and release the fabric, and we circumvent the RSA authentication method. As a side note, we can mitigate this attack, right, with enforcing the encryption, as we never triggered the encryption, right? So this is the part to defend. Okay, so let's come to a quick conclusion and wrap up the talk, right? So we can say we can fuzz effectively on hardware, as we found the Just Start attack and rediscovered the Starbleed attacks, and we gain a better understanding of the configuration engine. We have to do this efficiently, as we only can check these rather useful bit streams. So we need these fuzzing strategies, right? And what was also very helpful was this rapid prototyping approach. And as I said, the challenges was here really the scalability issue, right? Because hardware doesn't scale well. We need, for every fuzzer instance, we need a hardware, so an FPGA at our hand. And for ultra-scale, we have like 4, and we have like 15 of the 7 series FPGAs in a cluster, and then in parallel. So this doesn't scale well with like spinning up thousands of virtual machines and test there in parallel. So we need this reduced search, we have this reduced search space, so which we tackled with our strategies. And also, we have the problem of the state invisibility, right? So we only can read back these 32 registers, so we can get this whole internal state, right? So we have a slight invisibility here. And still, our process is human-assisted, so we want to tackle like these, especially these last 2 things in our future work. So we want first to include side channels, so to gain a bit more of the internal state visible. And also we want to have some kind of feedback, so this feedback-driven fuzzing approach and some other techniques known in this fuzzing world from software testing. Okay, yeah. Thank you very much, and I'm happy to take any questions, and also check out our Confuzz framework on GitHub, or ask Felix, is also here, who has done most of the implementation work during the coffee breaks.
Thank you, Mike, for the great presentation. So if you have questions, you can come either to the microphones or just raise your hand. Toon, you can start.
Yeah, Anton Penal from PQ Shield. Nice talk. I was wondering, because when you're fuzzing, you're looking for unexpected behavior, right? And in software, that could be a crash or an out-of-bounds memory access and so on. Could you talk a bit more about how you determine when an input generates a crash? You mentioned it's human-assisted, right?
Yes.
But I assume you didn't look at all the 72 million or whatever input bit streams manually. Yep. So could you talk a bit about that, please?
Yeah, sure. So we have this. Different strategies, right? So we have like in this 71 fuzzers. So we have like, for example, we set up one fuzzer for this control 0 register. So this is like one fuzzer, and then we started fuzzing the whole register. And in the first place, we started with fuzzing like most of the bits in this. And then we set this evaluation phase to see if there are any difference at all to the default state, right? And then we came back with like a lot of differences. And so we narrowed down then the different cases, like in this human-assisted process, and see, okay, if you can cluster some parts of the bits which flip, right, especially in the status bit. So there's one status register, which reflects the status of the FPGA, and if there's any kind of difference, right? For example, if there's the decryption bit enabled, right? Or if there's like there are two errors regarding the encryption, right? So if there's this encryption error of bit coming up, for example, and so we can narrow down like then the differences, right? And then see if there are any weird behavior, right? So this is like our crash, and then we loop it back to the case and see, okay, how the FPGA behaves. And then we have like a giant Excel table, which is also on the GitHub, where all the different cases we have is like written down, and how the different bit patterns are interesting, right?
Okay, thank you.
Yeah.
So thank you very much for the presentation. I wanted to ask regarding how basically dangerous this is. Like you said that you found a bug that you need to completely do the hard reset. Do you think that you were lucky at the end that there was only like that, or if you will pick the different FPGA manufacturer, you would be expecting more issues, even breaking the device?
Oh, you mean that you can brick the device, maybe? Yeah, this could happen, right? So yes.
But it did not happen for you.
Yeah, it didn't happen for us, right? So when we first hit this crash, we were like, hopefully it turns on again, right? So because they are like expensive devices, right? But yeah, we luckily not ended up in this, but this would be also a huge find, right? So if we can brick the device, this would be kind of bad, right? So this would also a bit, big problem, right? But anyhow, I would expect somehow that in like every device there is something, right? Usually. So, but the question is rather, this is tied to the efficiency, right? So, how can we efficiently fuzz hardware with limited knowledge, right? So this is kind of the problem here. So, in the problem space we are in.
And do you expect some logical breaking, like in a sense of, like I saw 100 of strange bit streams, I'm no longer continuing?
Yeah, maybe this can happen, right? I'm not sure if this happens, right? So you can brick your FPGA yourself, right? If you there are fuses which can brick the FPGA. So if there's this fuse to enable so to enforce the encryption and to disable the encryption, but this is intentional, right? So this is a tamper-resistant countermeasure, right? So this can be done, right?
Thank you very much.
Yeah.
One last short question, please.
Thanks, Mike, for the talk. So I was just wondering, have you tried this on like other devices? In particular, like what would be the challenges to, let's say, move it from a ultra-scale FPGA to a Zinc environment where you have an ARM and an FPGA working together?
So we tried mostly Xilinx, right? So we tried the 7 series and the ultra-scale series. For like 6 series, you would need to like change to 16-bit words, right? And for the ultra-scale, for the Zinc series, I would say this can be done, and we want to try it in like future work, because you can faster fuzz, right? And I would say this can be done quite easily because with BUFAs, this is everything is quite modular, right? So we have this hardware abstraction layer. Then you would just need to switch from OpenOCD to how is this called? This on-chip programming interface, right?
PCAP.
Yeah, PCAP.
right.
Genau. Yes. Yeah.
And but like, would you use like a similar fuzzer for both the PS and the PL, or like this is more for the PL part, and like you would use a classical technique for the PS part or something?
Oh, yeah. For the ARM part, I would say this this can also be like done with BUFAs, but I would say this is a kind of quite different because this is like classical CPU fuzzing, right? Right. Yeah, but this can also be done with BUFAs, right? Yeah.
All right.
Thank you.
Yeah. Let's thank Mike again.
Thank you.
And with that, we move on to the next talk. Our next speaker will be Jakob Feldkeller, and he will present the work Combined Threshold Implementations.
Yeah, thank you for the introduction. So this is a work I did with my colleagues Jan Richter-Brockmann, Pascal Sastrich, and Tim Gunesu. And yeah, so this paper is settled in the area of physical attacks. So whereas Mike said we need expensive equipment, and Colin would probably disagree. And so we assume an adversary that can observe the physical execution environment of a device under attack, and by that perform side-channel analysis. So for example, observing the power consumption or EM emanation or something like that. And we also assume that the adversary can control the execution environment of the device. So in that case, perform fault injection analysis, fault injections. For example, changing the clock signal or the power supply or something like that. And in particular for this work, we assume that the adversary can also do both at the same time. However, I don't care whether we need expensive equipment or not, because for this work we work in a formal model, so where we can argue about properties and make some formal statements and prove security. So how does such a model look like? So one famous example is the probing model, and we take a glitch extended version of this. And here basically the adversary gets access to a circuit or the structure of the circuit, and then can select a certain set of wires, of which then the glitch extended probes are given, values are given to the adversary, and those are all the stable signals to the probed wire, which usually are register or primary inputs. And then we say that a circuit is deprobing secure if up to D probes can be simulated without any access to the secret, which means that we can recreate the distribution of the probes, so of the observation of the adversary without knowing the secret, which then means that it is statistically independent of the secret. So to protect against this, we usually use Boolean masking or masking in general, and one form that I will talk about is Boolean masking. Probably most of you know this. Let me shortly recap it nevertheless. So here we assume that we have a secret Boolean value, x, and we replace this by a vector of different Boolean values, such that if we have a true subset of those values that we call shares, this is independent of the secret. And if we have the sum over all of them, then we know the secret and can recreate the secret. And then we don't perform computation about over the secrets, but instead over the shares in such a way that is hopefully deprobing secure. Second model that we can look at is for faults now is the threshold fault model, and here we assume that an adversary again knows the structure of the circuit and can select a certain number of gates in the circuit and change the underlying function of this gate to a with a predefined set of faults that you can do. And then we say that a circuit is k-fault secure if up to k faults can be detected or corrected at the output of the circuit. And to protect against, or to be secure in this model, we usually or one way to do this is simple replication, right? Performing an operation not only once, but for example 3 times to correct to be able to correct one fault by a simple majority vote. And then the last model I want to introduce is the combined model, which is simply the combination of both of them. So you have an adversary who knows, again, the structure of the circuit, can select a certain set of gates and manipulate the underlying function, and a set of wires that then the glitch-extended values are given to the adversary. And then we say that a circuit is DK combined secure if up to D probes can be simulated without access to the secret in the faulty circuit, and up to K faults can be detected or corrected at the output. Now, how would we protect against that, right? A trivial or a simple method would be to just combine, again, the countermeasures for the single one, so masking and replication. Is this secure? It turns out, no, it's not, right? Otherwise, I wouldn't stand here probably. And so there are mainly 2 reasons why that's not the case. The first one is that usually if we do mask circuits, we need some entropy to refresh the masking every so on. And if we, so for example, here have a probe at this position, then we don't learn anything about the secrets because we learn only 1 share for each value. Because of this register there in the middle where the probe ends, there is some randomness that refreshes the masking, and so we don't learn anything else. However, if we inject a fault into this randomness, then this refreshing doesn't work anymore, right? So the probe propagates further, and we learn the secret B in this case. The second type is something we call conditional fault propagation. So if we have, for example, a fault in this A1 here, which can be caused by some composition of circuits, right? Then an effective fault in this value will only propagate further through an AND gate if the other value is equal to 0, and is equal to 1, sorry. And through an XOR gate, it will only propagate further the fault if the other value is correct. And this means that at the output, we only have effective fault if the secret B is equal to 1. However, this alone doesn't help anything because the adversary doesn't know whether we have the faulty or the correct value here. So we cannot distinguish between correct and between an effective fault or an ineffective fault. However, if we have replication, right, and we have a probe that can observe 2 of those replications, or we have 2 probes that can do that, we can distinguish correct from an incorrect run and learn the secret B again. Yes. Now, in this paper, we want now to provide a method to construct combined secure circuits. And we do this by starting with a secure circuit against side channel analysis, constructed through a quite general design paradigm that I will outline in a second. And we transform this then via specific steps to a combined secure circuit. So the side channel secure circuit needs to be constructed according to the consolidating masking scheme, which is a method that tries to generalize different masking schemes to one scheme, basically. And so in CMS, they divide the circuit into different layers. So the first one is a nonlinear layer where we perform nonlinear operations. For example, here a few AND gates to compute the AND between A and B. And then we have a second layer that is the linear layer where we compute linear operations, right? Here an XOR, which XORs the shares of C. And the important thing here is that in those 2 layers, all component functions are non-complete, which means that any combination of D of those component functions are independent of at least 1 share for each secret. The third layer is the refresh layer, which we call in our paper isolation layer to prepare for the combined setting. And there we have a simple refresh of the the masking by adding random values to the component functions, basically. And then we have a layer of registers to stop glitch propagation. And then finally, the last layer is a compression layer, which just reduces the number of shares for the output. And now if we want to transform this to a combined secure circuit, we have 3 different steps that we need to take. The first one is to replicate the refreshing, so that that each value is refreshed by at least k plus 1 random bits. And by doing this, we ensure that if an adversary can place k faults, they cannot remove the entropy of this refresh layer, right? And so we ensure that at the end we definitely have a refreshed masking scheme. The second step is to replicate the circuit, right? So this means 2k plus 1 times is what we do, which allows us to correct at the end, which then means that we have standalone fault security. And the final step is to add corrections in the isolation layer. We do this by a majority vote, and the important thing here is so that the corrections have a property that we call fault isolating corrections, which means that the output is always independent of incoming faults, which is usually the case if you have 1 fault, and then you can use 1 correction, right? Because you either have a fault in the correction or at the input. But if you have 2 faults, then one normal correction does not work, because you can insert a fault such that the output is dependent on whether the input is correct or not. And this would give additional leakage, so we don't want to have that. So we need this property. And one way to do this is just have k consecutive corrections. But I mean, for higher order, this is quite expensive. So these are the 3 steps. Now, one question is, why is this called our paper called combined threshold implementations? And this is because the CMS is, as I said, a generalization of multiple masking schemes. One of them is threshold implementations, which is a bit better known probably. And here the idea is to have an isolation layer basically that does not consist of additional refreshing, but instead you have constructed the previous component functions that you have an uniform output at the end. And another variant basically of this, you can kind of say, is a paper that was published in 2000 and, I don't see it at the moment. So a few years ago, reconsolidating first order masking schemes, nullifying fresh randomness. And there the idea is quite similar. You again don't have a classical refresh layer, but you just ensure that the output, that you have joint independence between the input and the output, which allows you to be more efficient in the implementation. And for both of those variants, basically, you can also use our approach to transform those into combined secure circuits. Now, we did multiple performance evaluations in our paper, one of which I would like to discuss here, which is an AES implementation that is secure against 1 fault and 1 probe. And in this table, we first have 2 implementations of the S-box without any protection. Then we have 3 variants of side-channel secure variants that for CMS, TI, and NFR, so the 3 variants that we can transform to combined secure circuits. And then for combined security, we have 3 previous works basically, and then our 3 variants that we get from transforming the SCA variants. And I want to highlight a few things. So first of all, if we look at the area in gate equivalent, then we see that our approaches perform quite well. So we have two of the best implementations here. And yes. The other thing I want to highlight is that if we look at latency, then our approach doesn't add any registers, right? So we keep the latency performance from the SCA variants, which means that if you get better SCA masking schemes, then you also get better combined variance. And then for the randomness, so for this CMS approach, there we don't need to double the randomness. And the reason is that there are already mask refreshing that use more than one refresh per value for most of them. So we need only 8 bits of additional randomness to ensure that this is still the case, so that we have security in the combined case. And the last thing for the TI approach, they don't require any randomness in this implementation, so the combined thing also doesn't require any randomness, which is nice. Yes, so to summarize, we have a transformation from a SCR mask circuit that is designed according to the CMS design paradigm, and the transformation consists of 3 steps: refreshing the replication, circuit replication, and correction insertion. And then you have a combined secure circuit. And that's it. Thank you very much.
Thank you, Jakob. Do we have questions? You can step forward if you want to. For the meantime, I have a question. So you mentioned that you prefer using error correction over detection. Could you detail a bit on why that is?
Yeah, so because in error detection, you have the problem that you need to do something after detecting a fault, right? And we want to do this, I mean, we focus on hardware, right? This is why we do the glitch-extended probing model. And it is not trivial what to do after you detect a fault, because in software you can simply abort, right, and do nothing, and then you don't have any leakage anymore, probably. But in hardware, this is not the case, right? The circuit will still compute something, and you need to actively erase the computation, basically, to erase the additional leakage, and this is not that trivial. Yeah, so that's why we use correction.
Thank you. Maybe one other question as well. So in the beginning, you shortly discussed about practical attack scenarios where the countermeasure could help out. How would they look like, and how realistic do you think is it to go up in the orders, right? So maybe in maybe we start with the first question, right? What would they look like?
Yeah, so I mean, it's you would have a combination of classical fault and sidechain analysis, right? You would, I don't know, for example, have a laser pointed at your chip, or EM probe, right, pointed at your chip, and then induce the fault by that way, and then at the same time do power measurements and learn something, because the power measurement is different than if it is correct, right? But this is something that is still in the beginning of research, right? So there are some practical attacks against software implementations, but not so many at the moment against hardware, actually. But yeah, so this is something that
usually our probes are more statistical, right? So we have to repeat measurements. Doesn't
yeah, sure. No? But I mean, yes, you need then to see whether, I mean, you need then more measurements to have the faults at the right positions always, right, and so on, which makes it difficult. But yeah, definitely.
All right. Are there any further questions? Yeah, we have a few minutes. Let's say we otherwise wait shortly before we start the new talk for other people to come in as well. Well, in the meantime, let's thank Jakob one more time for the great talk. And then we'll just shortly wait. The next talk is also going to be a video talk, and but we have a person for responding questions after the talk, so please stay by. think we'll just wait a minute for people that might be switching between tracks, though I guess it's not that likely. So our next talk is going to be static leakage in dual rail pre-charge logics, and it will be presented by Bian Fadania. And I think we can slowly get started. Thanks.
Hello and welcome to the presentation. The title of the presentation is Static Leakage in Dual Rail Pre-Charge Logics. My name is Bijan Fadania, and this is a joint work with Torben Mus and my advisor, Professor Amir Moradi. Let's begin with a brief overview of static leakage. Leakage current is a current that passes through a semiconductor device when its components, which are transistors, are not actively switching. In several recent editions of CHES, researchers have presented findings showing that the static current of a digital CMOS is influenced by its input signals. Therefore, if an adversary can accurately measure it in a cryptographic device while the secret is present somewhere in the circuit, he is able to use this side channel to extract the secret from the device successfully. In older technology generations, most of the power consumed by a chip was dynamic power, and the share of the static power was not noticeable. However, with the downscaling of CMOS technology, the share of static power became larger and larger, especially for technologies smaller than 19 nanometer. Besides the increasing share of this side channel in nanometer devices, a static power side channel analysis attacker, or shortly SPSCA attacker, can enhance the signal-to-noise ratio by increasing the supply voltage and also the temperature. Moreover, the attacker is also able to hold the clock pulse for a long time and measure the static current multiple times. Then, by calculating the average of the recorded samples, the attacker is able to reduce the measurement noise. In this way, the SPSCA attacker can perform a successful attack with just a few number of samples. This work discusses the dual rail pre-charge logic, also known as DRP logic style. In DRP logic, every single bit is accompanied by its complementary value. Here you see an example of a DRP AND gate that receives two signals A and B and their complementary value as dual rail inputs and generates a dual rail complementary output. Each DRP logic cell has two working phases, one known as pre-charge and the other one as evaluation. Here we have a timing diagram of the DRP AND gate. As shown in the diagram, the working phases are synchronized with the clock pulse. In this example, when the clock pulse is high, the circuit is in the pre-charge phase and all dual rail signals are pre-charged to the predetermined value. Here the predetermined value for the pre-charge phase is 0. When the clock pulse is low, the circuit is in the evaluation phase and all the dual rail signals, including inputs and outputs, have their complementary value. If we look at the complete timing diagram of the AND gate, we observe a constant number of transitions in this logic style for all clock cycles. The other benefit of using DRP logic is that the logic style is completely glitch-free because of the pre-charge phase. Besides these benefits from dynamic power consumption point of view, this logic style mostly suffer from early propagation effect or data-dependent time of evaluation. Another challenge in DRP logic style is that this logic style may suffer from unbalanced dual rails. This work deals with improved masked dual rail pre-charge logic style, or shortly IMDPL. Before introducing IMDPL, MDPL was introduced to address the issue of unbalanced routing. Here you see a two-input MDPL AND gate. As you can see, in addition to the dual rail signals, this gate also receives a single bit dual rail mask bit. Because of using the mask bit, MDPL logic cells are able to swap the signals of each dual rail randomly at every clock cycle. Therefore, MDPL doesn't need balanced dual routing. but still suffer from early propagation effect. To address the early propagation effect in MDPL, IMDPL was introduced. If we compare the IMDPL AND gate with the MDPL one, we notice that in IMDPL there is a combinational circuit at the gate inputs. This combinational circuit examines if all given inputs are in the evaluation phase to pass the inputs to the cell, or all of them are in the pre-charge phase to let the cell also move to the pre-charge phase. Despite all the optimization in MDPL and IMDPL, since the dual rail mask signal is connected to all IMDPL cells, it has a relatively high capacitance. Therefore, if mask signals are routed independently of each other and have different capacitances, their transition at the start of evaluation phase and also the pre-charge phase becomes distinguishable by observing the dynamic power consumption. And the adversary can divide the traces into two separated groups based on the mask value and then perform a SCA attack on each group separately. In this way, the adversary can remove the entire effect of the mask. In this study, we present the result of an experimental evaluation of the security of DRP-protected circuits with respect to SPSA attack, and introduce a slightly adapted instance of such a scheme, specifically optimized to prevent them. As I mentioned in the previous slide, here we focus on IMDPL logic stack. Beside the IMDPL and the optimized version of it, which we will see it in the following slides, we have implemented a probably secure threshold implementation based hardware mask cryptographic core using both IMDPL and its optimized version. In other words, our ASIC in this work has 4 different cores. One based on the IMDPL style, the other one based on the optimized version of IMDPL, and 2 hybrid cores using a threshold implementation based on 2 previously mentioned logic styles. All the analyses in this work are based on the serialized hardware implementation of a block cipher present AT, which is shown here. As it is shown, it consists of a key and a state register, some control logic, and also 1 4-bit box. As I mentioned, our study is based on an experimental analysis. To this, we have developed an ASIC prototype chip designed and fabricated in 65 nanometer CMOS technology. Here you can see the layout and also the microscopic photo of the manufactured and bonded die of the ASIC that we have developed for our investigations. The CASA depicted in the microscopic photo is the name of an excellence cluster at the Royal University Bochum with a focus on IT security research. This project was also funded by this cluster. We performed our measurement using a custom measurement board. Here you see its picture. This board has 2 separated parts. On the left side of the board, an FPGA, which is responsible for managing the measurement procedure, is located. And the ASIC is located at the right-hand side of the board. To increase the SNR, we perform all measurements at a temperature equal to 19 degrees Celsius. We also held the temperature fixed at this level to reduce the measurement noise. To this end, we use a climate chamber as shown in this photo. To measure the static current, we used a source meter. A source meter is able to work as a power supply and also high precision current measurement instrument simultaneously. Here I am going to explain about our evaluation method. We used a fixed versus random t-test for the leakage assessment. This leakage assessment only reveals a detectable leakage in the collected samples. Therefore, to investigate the exploitability of the leakage, we used a moment correlation DPA attack. We start our evaluation with IMDPL cell. Because of the time limitation, I cannot show all the results of our analysis here, and only the noticeable ones are shown in this slide. Just as a reminder, in the static power side channel analysis, the attacker can hold the clock pulse and measure the static current. Based on this assumption, we hold the clock pulse in two different working phases of the IMDPL circuit. It means we have separated results related to both evaluation and also pre-charge phase. On left, you see the attack results when the chip is in the evaluation phase. In this case, we were able to perform a successful first-order attack with around 5,000 samples. But in the case of the pre-charge phase, a successful second-order MCDPA attack needs almost 300,000 samples. It is clear from the previous results that the device leaks strongly in the evaluation phase. In the evaluation phase, all the dual rate signals have complementary values, and the observed first-order leakage originates from the combinational blocks. But in the pre-charge phase, the situation is different, and all dual rate signals are pre-charged to zero. Actually, in the pre-charge phase, we have only some stored values in the flip-flop. So let's look at the structure of an IMDPL flip-flop. The IMDPL flip-flop, as you can see, consists of some combinational logic cells and one single rail flip-flop. The only part of the circuit that is not pre-charged is the single rail flip-flop. This flip-flop stores a mask value of D with the mask bit M of N. Therefore, a second order joint leakage in pre-charge phase is exploitable through this single rail flip-flop. Let's summarize our analysis results. We have demonstrated that the information leakage during the pre-charge phase is lower than during the evaluation phase. Our finding also revealed that the second order leakage in the pre-charge phase comes from the single rail flip-flop. Based on these results, in the following slides, I will show you an optimization method for IMDPL logic style to prevent SPSC attack. Let's start the optimization part with an introduction to different types of clock pulses. We can divide the clock pulses in three different groups. The first one is a standard clock pulse, which we know as an astable clock pulse. This clock pulse has no stable states and continues to switch between high and low. The second one is a bistable clock pulse. This clock pulse has two stable states and needs an external trigger to change its states. As an example of this pulse, we can refer to a clock under the control of an attacker. While the attacker can hold it on the required level, both levels, high and low, are stable. There is also another type of clock pulse, which is known as monostable clock pulse. This clock pulse has only one stable state. Imagine a clock pulse that you can hold it on one predetermined level, and when you try to keep it on the other level, it goes to its stable state after a while. Therefore, a monostable clock pulse can always force the device into the predetermined phase when the clock is paused externally. Here, a simple circuit is shown which is able to receive an external clock pulse in its input and generate a monostable clock pulse at its output. The circuit has an inverter, an OR gate, and also a delay line. The delay element in the monostable clock circuit can be implemented by connecting a couple of inverters in series. Knowing the critical path delay of the targeted circuit, we use the Synopsys HSPICE simulator along with the similar 65nm commercial library to determine the minimum number of required inverters. The circuit is triggered with the negative edge of the external clock pulse and generate a high-low high pulse at the output, which lasts for a time equals to T. The duration of the generated pulse at the output of the circuit is equals to the delay line of the circuit. Selecting the appropriate duration of delay T is important. The duration of T must be long enough to permit the combinational circuit to complete the evaluation process. which means it should be larger than the critical path delay of the circuit. Here you see if the adversary tries to hold the external clock at 0, which is the evaluation phase of the core, the internal clock will stop at 1 or high, which is the pre-charge phase. And if the adversary holds the clock pulse at high, the internal clock pulse will stay at high. The next optimization is related to the IMDPL. We mentioned that the joint leakage of the mask D with the mask bit M of N is exploited through a second-order SPSC attack. But if we replace this single-ray flip-flop with two single-ray flip-flops, same as this new structure, the flip-flop always stores both complementary values. Without intra-die process variation, such a structure would potentially mitigate this second-order data dependency. In other words, if both single-ray flip-flops are realized identically in silicon, the exploitability of the second-order leakage at the pre-charge phase should be prevented. We name this optimized version of IMDPL flip-flop as a static robust IMDPL, or shortly SR-IMDPL. To see the effect of using SR-IMDPL, we have a comparison between IMDPL and SR-IMDPL in the evaluation and also pre-charge phase. In the evaluation phase, IMDPL and also SR-IMDPL shows a strong data dependency through a static power side channel. This confirms that the first order leakage in the evaluation phase originates from combinational circuits. As it is shown here, in the pre-charge phase of SR-IMDPL, to detect the second order leakage, 700,000 samples are needed. Actually, this data dependency originates from the intra-die process variation. Based on the previous results, it may not be sufficient to rely on such a hiding countermeasure method. Therefore, we have evaluated the effectiveness of algorithmically masked cores realized by DRP logic styles. To investigate the effect of such a threshold implementation using the IMDPL and also SR-IMDPL without the effect of single bit mask, we set the mask bit to 0. Here you see the result of fixed versus random t-test for threshold implementation of IMDPL and also SR-IMDPL. In both evaluation and pre-charge phase, as you see, the best results related to the threshold implementation of SR-IMDPL in the pre-charge phase. This slide shows the results of the threshold implementation of SR-IMDPL when its single bit mask is random. I mean, the mask bit is not fixed and it changed randomly. The left image shows a second order data dependency in the evaluation phase with around 1 million samples. However, in the pre-charge phase, we didn't detect any data dependency up to the third order of statistical moments with 12 million samples based on the t-test. We evaluated the security of combination of the probably secure first order threshold implementation and SR-IMDPL against classical dynamic power SCA attacks. In this slide, the results of such an investigation are shown. We used a digital oscilloscope at a sampling rate of 2 gigasample per second. Due to the very low amplitude of the signal, we also employed an AC amplifier with a gain of 10 dB to collect the traces with lower measurement noise. In the case of IMDPL and SR-IMDPL, we detected data dependency with less than 50,000 samples. However, in the case of threshold implementation of SR-IMDPL, we didn't detect any data dependency up to third order statistical moment based on the t-test using 100 million traces. In this slide, the post-layout analysis results of all 4 cores using Synopsys IC design flow are shown. Here, all the calculated overhead factors are based on a comparison of each core and the unprotected core. In the case of non-mask cores, it is noticeable that the overhead of SR-IMDPL is not too high compared with the IMDPL. Actually, the monostable clock generator is a small single circuit and does not add much overhead to the design. And the overhead is mostly caused by inserting an extra single ray flip-flop inside an IMDPL flip-flop. As a conclusion, it was the first experimental evaluation of the security of DRP protected circuit with respect to static power side channel analysis. We introduced an adapted instance of IMDPL optimized to prevent SPSC attacks. We have also learned that hiding or masking alone seems to not able to protect sufficiently against this threat, and strong protection can be achieved with hybrid countermeasure. However, the cost of overhead of the hybrid countermeasure is significant. Thank you for your attention.
Yeah, you already did thank Bian, who could not be here due to visa issues, unfortunately, in person. So, are there any questions? So we have Amir here as well. He can, maybe just come to the front and share the mic, or you can go there. Be nice. Okay, awesome. So, are there any questions? You can step forward to the mic if a question comes to mind. Amir, maybe you could add 2 or 3 more sentences on the static leakage scenario. I would especially be interested in, I mean, we have seen that the costs for a strong countermeasure in this scenario is quite expensive. How difficult is it to get the modern chips into a state where the clock does not work anymore? We have many microcontrollers that have clocks included, so they are more difficult to stop, right? Maybe you could comment.
Yeah, one thing is for static power measurements, you need to stop the clock and then measure the static power. It means that how much current is passing through the circuit. Yeah, and then if you are not able to stop the clock, I mean, then it doesn't mean that you don't have any chance to perform a static power. It depends also on the implementation. There is, I think, a paper, again, by my group, I think 2 or 3 years ago, again at CHES, showing that even if you don't stop the clock and you don't care much about the internal state of the circuit, means that you don't stop the clock, but then, for example, the encryption is completely done, performed, but the circuit stops, means that the registers are not updated, but of course the clock is still running, yeah, but the registers are not updated, and then the registers contain actually the sensitive information, but actually the encryption is already done, and you don't clear the state, yeah, of the registers. If you don't clear the registers, still you can perform the static power analysis without stopping the clock, yeah. Because this state of the circuit depends again on the values which are stored in the register, and they affect the amount of the static power consumption, yeah. But if the circuit is very complex, means that, for example, you have some kind of internal clock sources and something else that, and then we cannot really assure that the state of the circuit doesn't change, then you don't have much chance to measure the static power consumption. Yeah? And then here what we have in this work was just like this, that you have you have the capacity, and the attacker is strong, can stop the clock. But then in dual reg logic, if you stop the clock and use a monostable clock, then again the circuit goes to a state that it mitigates the amount of static power or dependency, and then you may actually increase the security against these kind of attacks. I mean, it's not a perfect solution, but I mean it mitigates some form of the leakage.
Thank you. So there's one more question. Is it on? Try one more time.
My question would be, so if I'm the attacker and I want to attack a chip, and I can choose between analyzing the dynamic and the static power consumption, why should I go for the static one if it's so much more complicated?
Because it's low noise, yeah. Because it's for every measurement you get actually the amount of DC shift of the signal, and then you can wait enough for every measurement and get a very long signal and get an average to get a singular value, and then you actually have a very high SNR signal, yeah, with very high SNR, and then you can actually reduce the number of samples that you need compared to dynamic, but of course the measurement time is probably comparable or even longer to the dynamic. No?
So if there are no further questions, let's thank all the speakers of the session again, and Amir for answering the questions as well. Thank you for coming up. And this ends the hardware security session number 2. Yeah, next up is a track switch where you get a few minutes of a head start. Enjoy.